All right, this is the first video in a 3-video series on probability. And surprisingly, we're not discussing probability at all in this first video. We're just discussing counting principles, like how you count the number of ways different things can happen, which is really, in my mind, fundamental to how we do probability. So we're going to start off with some counting principles. We'll talk about tree diagrams, how to describe all those possibilities. We'll talk about what permutations are and what combinations are. Now, some of you may have learned about some of this already. If so, fantastic. If not, then this will be your first exposure to it. Okay, by the end of this video, I hope you're able to use the fundamental counting principle to answer questions about the number of ways things can happen and illustrate them using tree diagrams, and also understand what permutations and combinations are and how you're able to calculate them. Okay, the fundamental counting principle. If you have two events and one can occur in m ways and the other can occur in n ways, then the number of ways that they both can happen is m times n. Okay, we'll see a couple examples in a second. If you have 3 events or more than 3 events, if you have, for example, the first event can happen in m ways, the second can happen in n ways, and the third can happen in p ways, then the number of ways that all 3 can happen is m times n times p. And I think you can see how this can be expanded to 4, 5, or even more events. Okay, here's an example. You are framing a picture, and the frames are available in 3 different styles. Okay? Each style is available in 5 different colors. Okay? And if the mat board is available in 2 different shades of blue, how many different ways can you frame the picture? Okay, well, let's think about this. I'm going to draw a tree diagram to help me illustrate this. If I have 3 different styles of frames, okay, if I happen to choose frame 1, I could then choose from the 3 different colors of that frame. I'm sorry, 5 different colors. So I have color 1, color 2, oops. Okay. Now, that's not only for frame 1. It can also be those 5 colors could also be chosen for frame 2 or frame 3. Let me just group this a little bit. Okay. Okay, so 3 different styles of frames and 5 different colors for each one. Now finally, we can choose our mat board with 2 different shades of blue. Now I won't kind of write them all out, but you get the idea of there's 2 here, 2 here, 2 here, 2 here, 2 here, and all the way down. Okay, so the number of ways that we can choose a frame in this context, where 3 frames, 5 colors, 2 mat boards, is going to be 3 times 5 times 2. Okay, so we get a total of 30 different choices, which happens to be 3 times 5 times 2. Okay, example 2, a Japanese license plate consists of 1 hiragana symbol. There are 42 possibilities, and then there are 2 different 2-digit numbers, 0 to 99. What is the total number of license plates that could be created using this system? Now, if you're good at Japanese and you realize that there are actually 48 possibilities, I guess there's only 42 of them that are used on Japanese license plates. At least that's what Wikipedia said. And so the number of ways that we could make license plates would be 42 times, let's see, there are actually 100 numbers here from 0 to 99. So if we multiply these three together, we get 42 with 1, 2, 3, 4 zeros. So we get 420,000 different license plates that could be created using this system. Okay, permutations. Now, if you take a group of n objects and you want to know how many ways that you can order those n objects, it's called a permutation. Okay, so if we want to order the letters A, B, and C, we could order A, B, and C. We could leave A the same and switch C and B. We could have B be first and go AC, or B and then CA, or we could have C AB or C BA. And those are the only possibilities. Okay? And the way I think about it is that we have three choices for our first letter. So my first letter can be either A, B, or C. I have three choices. Now, once I use one of them, I only have two left. Okay? And then once I choose the second letter, I only have one left, so it has to be the last letter. Okay? So it's 3 times 2 times 1, or 6 different ways of ordering the letters A, B, and C, or ordering any three objects. Okay? Now you'll notice it's 3 times 2 times 1, and I think you can understand that if we had like 4 letters or 4 objects, it'd be 4 times 3 times 2 times 1, which leads us into this idea of factorials. Okay? Factorials are written with an exclamation point. Okay, but basically it's that number times each number that's previous to it until you get down to 1. Okay, so for example, if there are 6 athletes running a 100-meter heat, how many ways can these 6 athletes finish? Well, in first place, there are 6 possibilities. And once that person finishes, there's 5 possibilities for second place, and 4, and 3, and 2, and 1. Okay, which is 6 factorial. So if 6 times 5 times 4 times 3 times 2 times 1 is 720. How many ways can 3 of the athletes finish first, second, and third places? Now, before I get into that second part, let me show you on your calculator, there's a factorial button if that ever comes in useful to you. So here's a calculator. If you could ever click math, click math, and I usually just use the left arrow to go back to this probability option. There is number 4 is a factorial button. Okay, that can be used. So if I wanted to, let me quit. I could do 6, math left 4, enter. 720. Okay, next question, which leads us into more about permutations and how to use it in more situations. How many ways can 3 of the athletes finish first, second, and third places? Now, if I only care about the first, second, and third, and I don't really care about the others, then I'm looking at 6 times 5 times 4 times 3 times 2 times 1 divided by, now I don't care about who came in 4th, 5th, or 6th. And so I need to kind of eliminate those 3 possibilities, which is 3 times 2 times 1. So in other words, I'm only looking at the first 3 numbers, because there's 6 ways that the first place could happen, 5 the second, and 4 the third, and that's it. I don't care about 4th, 5th, or 6th place. So it'd be 6 times 5 times 4, which is 120. Okay, this kind of expanded or generalized into a formula is n factorial over n minus r factorial, where you have n objects taken r at a time. So the last example we just did could have been written 6p3, because you have 6 athletes, and you're looking at how many ways you can order 3 of them. Okay, another example. You are burning a demo CD for your band. Your band has 12 songs stored on your computer. However, you want to put only 4 songs on the demo CD. In how many orders can you burn 4 of the 12 songs onto the CD? Okay, let me just preface this with talking about the fact that the order matters here. We'll get into the fact where, what if the order doesn't matter? But here the order does matter. So we're using a permutation. Now I have 12 objects, and I want to pick 4 of them. And so it'll be 12p4, and the formula is 12 factorial over 12 minus 4 factorial, or 4 factorial. I'm sorry, I'm wrong. It's 12 factorial. 12 factorial over 8 factorial. Now, instead of multiplying 12 times 11 times 10, I'm just going to use my calculator and do 12 factorial divided by 8 factorial. And I get 11,880. Okay? Now, the number of distinguishable permutations of n objects where one object is repeated s1 times, another is repeated s sub 2 times, and so on. Okay? I'll show you an example in a second, but this is the formula that we're going to use. Okay, find the number of distinguishable permutations of the letters in Miami. So, Miami has 5 letters, okay? But where M is could be replaced with the other M. So if I wrote Miami this way and happened to switch these 2 letters, it would still be written the exact same. Okay? So I need to take out all of those combinations, which is 2 factorial. And the same thing's true for I. I need to take out the duplicates of I. So if I take 5 factorial over 2 factorial divided by 1 factorial, I get $60. So there's 60 ways of 6 distinguishable permutations of the letters in Miami. Example 2, the number of distinguishable permutations of 2 red balls, 3 blue balls, and 1 yellow ball. Well, there are 6 total balls, so 6 factorial, but I need to take out all the repeats, okay? And that will be 2 factorial, 3 factorial, and then you could put 1 factorial, but 1 factorial is just 1, and so we kind of leave that one out. So I have 6 factorial divided by 2 factorial, 3 factorial, and I again get 60. Okay, this is permutations where the order matters. Now, if the order does not matter, we use combinations. Now, in our class, combinations are used quite a bit, and we'll come back to combinations, and our textbook writes it this way. Okay, let me back up real quick. I forgot to mention the fact that our calculator can do permutations in them using this formula. If you look at under that math, this you see number 2 is a permutation, 3 is a combination, and the way you plug that in is you put in n first. So 6, 2, 3 would be 6 objects taken 3 at a time. And that would give you the answer, okay? Okay, so our calculator uses NCR, but our textbook, and in most college classes, they use this NR symbol. In fact, I'm going to kind of stop this video right here because I'm getting close to 15 minutes, which is my cutoff for posting it in YouTube. There will be 2 videos for this first lesson. So watch the second video.